Okay, let's go ahead and get started. Today we're going to continue our discussion and finish our discussion of the Lagrangian formulation of general relativity. And much of today's class will focus on the variety of sorts of actions that one can write down for field theories, which will act as sources appearing on the right-hand side of Einstein's equations. So we'll be discussing two different kinds of matter that can contribute to the energy and momentum that appear on the right-hand side of Einstein's equation and act as a source for the curvature of space-time. So let me just remind you of where we left off last time. So we wanted to write down an action for the theory of general relativity. The dynamical variables that describe general relativity are the metric of space-time. And so the action will have to be a functional that depends on the metric of space-time. And it will be the sum of two terms, the first of which is the Einstein-Hilbert action, which describes the dynamics of the curvature of space-time. And then there'll be some matter part of the action, which will describe all of the other stuff that will act as a source for the curvature of space-time. And the Einstein-Hilbert action is equal to a constant, 1 over 16 pi g, where g is Newton's constant, times an integral. And the only thing that you're allowed to integrate in relativity in a coordinate invariant manner is a scalar, or more precisely, the square root of minus the determinant of the metric times a scalar. And the only scalar you can construct, which is second order in derivatives of the metric, is the Ricci scalar. So this leads us to conjecture that the integral of the Ricci scalar is the action, the appropriate action of general relativity. And the matter action is as yet unspecified. It sort of depends on what situation you're considering. In principle, the matter action should be the action of the standard model of particle physics, for example, which we believe describes all of the other known particles and fields in the universe. Often we will be more modest and not consider the entire standard model of particle physics, but just some parts of the standard model. And this matter action will depend both on the metric g mu nu of spacetime, as well as on whatever other fields are present in the theory that we're trying to describe. And so I'll describe today a few different possible forms for this matter action and the resulting equations of motion and stress tensors. And the equations of motion which follow from this action are obtained by minimizing with respect to the fields, to the degrees of freedom, and in particular the equation of motion for the metric is found by minimizing with respect to variations of the metric. So you compute the variation of the action to linear order in a variation of the metric, and you set it equal to 0. And what you find Einstein's equation. So the Einstein tensor, r mu nu minus 1/2 g mu nu times the Ricci scalar, is equal to 8 pi g times the stress tensor T mu nu. And T mu nu here is found by varying the matter action with respect to g mu nu. So T mu nu is a constant over the square root of the determinant of the metric times the variation of the action with respect to the metric. So at this point, you could now go ahead and write down the stress tensor for your favorite theory of physics. So the procedure for writing down the stress tensor is straightforward. We just write down the action. First, you could write down the action for your favorite theory of physics in Minkowski space. Then you covariantize it the way that we have learned to by changing partial derivatives into covariant derivatives and Minkowski metrics into curved metrics. And then you vary with respect to the metric. And the linear term in that variation is proportional to the stress tensor. So last time we discussed perhaps the simplest type of term that we could think of as a matter action, which was the case of a constant. So let me just remind you how that went. So for example, if the matter action is just equal to a constant in special relativity, then the appropriate covariantization of that in general relativity, so we remember that the integral of a constant is not something that makes sense in general relativity. Instead, the only thing that you can integrate is the square root of minus g times a constant, which we conventionally normalize to be minus lambda over 8 pi g, where lambda is just a constant, which is known as the cosmological constant. Then varying this with respect to the metric, so let me remind you that the variation of the square root of minus g, well, what was that? That was just proportional to the square root of minus g. I just want to make sure I get all the factors right. This is what we derived last time. So it's minus 1/2 times the square root of minus g, g mu nu, delta g mu nu. So that means that the variation of this matter action, which is just a constant with respect to the metric, will give you something proportional to the metric itself. So that T mu nu is just equal to minus lambda g mu nu. And so this is the simplest possible stress tensor that one could consider as a source term for Einstein's equation. And that's a stress tensor that's just proportional to the metric. And we discussed also the physical interpretation of the cosmological constant. It's just an energy and a pressure which are associated to the vacuum of space-time. An energy and a pressure which are associated with empty space. And in fact, it's a positive energy and a negative pressure. Or one can indeed consider cases where lambda is negative, in which case the cosmological constant would describe some matter with negative energy and positive pressure. And the cosmological constant is something that we will return to later on in our discussion of cosmology, and we'll discuss both the theoretical and observational evidence for a cosmological constant. But what I would now like to do is just complete our discussion by asking what other sort of matter could be present, which we could use to act as a source for energy and for stress energy in the equations of motion of general relativity. But before I go on and do that, let me pause and see if there are any questions. No questions? Yes?
That expression should be divided by 8 pi g?
I have factored, you mean this here?
No, the energy stress tensor.
Oh, I'm sorry, you're right. Let me put 8 pi g here. Yes, the thing that lives, so thank you, the thing that lives on the right-hand side of Einstein's equation. So that Einstein's equation would set this equal to g mu nu. Thank you. Any other questions? Okay, so what is the next simplest sort of matter that we could consider? So, we are discussing here field theories where we have a number 1 or more degrees of freedom per point in space-time. And the field theory that you are probably most familiar with is electromagnetism, where we have 4 degrees of freedom per point in space-time, 1 electric potential and 3 vector potentials, which you could combine together into a vector or a one-form per point in space-time. But in fact, there's an even simpler sort of matter that one could consider, which is known as a scalar field. And so that would be the case where our matter degrees of freedom are given by a scalar field, so that is to say a field phi, which would just be a function of points in space-time. So this would be the simplest type of field theory that one could possibly consider. And it's a scalar simply because phi will transform as a scalar under coordinate transformations. So our action then our matter action will be a function of the metric as well as the scalar degree of freedom phi. And it will take the form of the integral d4x root minus g of some Lagrangian, which will be a function of the scalar field and possibly its derivatives. And the stress tensor will be obtained by varying this action with respect to the metric and setting it equal to 0. And the equation of motion for phi will be obtained by varying this with respect to phi and setting it equal to 0. So I think it's actually worth, you may or may not have seen this, but I think it's actually worth understanding how to derive the Euler-Lagrange equations by varying L with respect to phi and setting it equal to 0. So have you guys seen this before? I know that in your mechanics classes you saw how to derive field equations in general, how to derive equations of motion by setting variations of the Lagrangian equal to 0 for single degrees of freedom. It's only a hop, skip, and a jump from there to understanding how to write down Euler-Lagrange equations for things like scalar fields, which have 1 degree of freedom per point in space-time, rather than 1 degree of freedom that's a function of time. But it's something that can be a little confusing the first time you see it. So let's just go ahead and understand how that works. So even before considering the coupling to gravity, what I would like to do is just consider a scalar field phi in Minkowski space. So then our action, we'll forget about the metric dependence, will just be a function, the integral of some Lagrangian. And as usual, I will take this Lagrangian to be a function of phi and its first derivative and not any higher order derivatives. This is just an analogy with the usual statement in mechanics that our equations, our action will be a function of our dynamical variables and their first derivatives. And so the equation of motion for phi is found by varying phi to first order in some variation and setting that variation equal to 0. So this is something that we did yesterday for the case of a metric, which was a more complicated set of degrees of freedom. And I think it's worth reiterating for the case of a scalar field. So let's imagine varying this action. So first of all, let me pause and see if there are any questions. And also, let me flip to the right page in my notes. Good. Okay. And no questions? Okay. So how will this action vary if we vary phi in order to find the equations of motion for phi? Well, to first order in the variation, there are two possible contributions that you need to take into account. So L will depend both on phi and its first derivative. So you need to take first the derivative of the Lagrangian with respect to phi times delta phi. So that's just the variation of the Lagrangian due to its dependence on phi. And you also have to add to that the variation of the Lagrangian due to its dependence on the derivative of phi. So there are four possible derivatives of phi, where the index mu here will run from 0 up to 3. So that means that there are four possible terms that you can write down which will describe the variation of the Lagrangian due to the variation of the derivatives of phi. And what are they? Well, to first order in the variation, they'll be the derivative of the Lagrangian with respect to d mu phi, and then that will be times, using the chain rule, the variation of d mu phi. And here the index mu is summed over as usual using the Einstein summation notation. So is the origin of this equation clear to everyone? All I'm doing is using the chain rule from multivariable calculus here and saying that there are two possible sources for the variation of the Lagrangian if I vary the field. The first comes from the dependence of the Lagrangian on the field, and the second from the dependence of the Lagrangian on the variation of the field. And now, if phi goes to phi plus delta phi, then d mu phi goes to d mu phi plus the derivative of d mu phi. So that means that the variation of d mu phi is equal to d mu, the variation of phi. That's an almost tautological statement, but it's one that can be a little confusing sometimes. So what that means is that this term here on the right-hand side of this equation can be written as the derivative of d phi, of delta phi. Okay. So is this clear? Is everything that I have done here clear so far? So now what we can do, what do we have here? The second term that we have here is the derivative of the Lagrangian with respect to d mu phi times a derivative. So we can integrate that by parts. And what is this? This is then the integral d4x of the derivative of the Lagrangian with respect to phi minus the derivative of the derivative of the Lagrangian with respect to d mu phi, all times delta phi, plus a boundary term, which comes when we integrate by parts. Or if I wanted to use more fancy language, I would say it's the boundary term that we obtain by using Stokes' theorem. Stokes' theorem is just the higher dimensional version of integration by parts. Is that clear to everyone? So all I'm doing here is integrating this expression by parts. And there'll be some boundary term that appears, which I will neglect as I usually do when I extract the equations of motion from a variational principle. Yes?
Shouldn't boundary term be 0? Because when you vary some function, you said that we don't
yeah.
y
Yeah.
is fixed at the point.
Yes. So that's what I was going to say next. So usually when we describe functional derivatives using a variational principle, what we do is we hold fixed the value of the function at the boundary, and then we only vary in the interior. And so for that reason, that's why I'm neglecting the boundary term, because if I only consider variation, if I consider this action defined on some region of space-time, and I vary delta phi I vary phi in the interior of that region, but I set its variation at the boundary to be 0, then indeed this boundary term will be 0, as you said. So that is why I'm going to set this equal to 0 and ignore it. Good question. So this gives us an expression for the functional derivative with respect to our field phi, it's dl by d phi minus the derivative of L with respect to d mu phi. And that will be set equal to 0 if we wish to obtain an extremum or a local extremum of this action. And the resulting equation of motion is the Euler-Lagrange equation, which is the equation of motion for the field phi. And if we had more than one field in our theory, then we would obtain one equation of motion for each field, which is found by varying the action and setting it equal to 0 for the variation of each different field in the theory. Sorry, that sentence was phrased a little confusingly. If we have more than one field, then we vary the action with respect to each field and obtain an equation of motion for each one of these fields. So in order to write down the action of a scalar field theory, for example, we then need to decide what kind of Lagrangians will be acceptable. Before I go on and do this, let me pause and see if there are any questions. So this equation that I've written down is hopefully very familiar to you. If I had a phi which is a function only of time and not of space, then this would be exactly the Euler-Lagrange equation that you see in your mechanics classes, where you have a total time derivative here, and then the derivative of the Lagrangian with respect to x dot. The only difference here is that we're now considering a theory where we have 1 degree of freedom per point in space-time, so we also have some spatial derivatives that appear here as well. But the derivation goes through exactly as it does in the case where you have only a finite number of degrees of freedom. So what sort of Lagrangians can we write down? Well, the basic principle that we would like to impose is the same one that we were using yesterday when we were writing down the action of general relativity. Well, the action should be second order in derivatives of phi, and it should be a scalar under coordinate transformations. So, if you think about it, then the only thing that it can be involving the derivatives of phi is the square of the derivative of phi. So d mu phi is a vector. The only way you can make a scalar out of a vector is by squaring it. And you could take some higher power, of course, but that would no longer be quadratic in the derivatives of phi. And the only other scalar that you could imagine forming from the scalar field phi would be phi, or more generally, some function of phi. And so the Lagrangian in general could have two terms. It could have this term involving the derivatives of phi, but it could also have a term involving some function of phi. And in analogy with particle mechanics, we will call that v of phi, where v is a potential. So this first term is a kinetic term, and the second term is a potential term. And you should think of this as being completely analogous to the standard kinetic and potential terms x dot squared minus v of x that you would see in your standard mechanics classes. Okay, and actually, there's a conventional factor which we put out in front of minus 1/2. Of course, any numerical factor that we put out in front can be removed by rescaling your field phi in some way. So that's just a convention. In order to make it look even more like the expression for the Lagrangian in particle mechanics, L is 1/2 x dot squared minus v of x. Question?
Why are we limited to quadratics?
In principle, you could write down actions which are not quadratic in the derivative of phi. Those would involve a higher number of derivatives. And so the equations of motion that you would get would involve more than just two time derivatives. And in most theories of physics, the equations of motion involve only two derivatives. So that's why we're restricting our attention at this point to such theory, only to such Lagrangians. You could, of course, ask me, why couldn't I consider a Lagrangian which looks something like phi squared times d phi squared? That's also a scalar. It's also only derivatives of phi. And the answer is that you could consider such a thing. If this were a class in quantum field theory, I would mutter words about effective field theories at long distances, but this is not such a class, and so I will not mutter those words, but I will only say that there's a particular logic you can use which will guarantee that if you study physics at long distances, then this kinetic term, as I've written down here, will be the leading contribution. Any questions? So, in fact, a scalar field is not some crazy abstract object that you only write down by thinking formally about transformation properties and formal nonsense like that. A scalar field is a very physical thing. For example, if you imagine that you have some crystal or some solid, and you look at the excitations of this crystal, then the low energy excitations will be what are called phonons. They will be scalars in the sense that they are just describing some displacements that don't transform in any interesting way under coordinate transformations. And indeed, the action which governs those dynamics is precisely the sort of scalar field action that I've written down for you here. Or even more prosaically, if you took a guitar string, for example, and you looked at the fluctuations and the dynamics of the motion of that guitar string, it would exactly be described by this scalar field that I've written down here. It would be a scalar field in one dimension if you're studying a guitar string, one spatial dimension if you're studying a guitar string, two spatial dimensions if you're studying the fluctuation of a drum, three spatial dimensions if you're studying the fluctuations of a solid or a crystal or something like that. So these scalar fields are indeed very physical things, and they arise all the time. And indeed, we believe that there is a scalar field, at least one scalar field present in the fundamental Lagrangian of nature. One scalar field that we're pretty damn sure is there is known as the Higgs field. It's a scalar field. It has an action which looks identical to the action that I have written here. It has some other interactions with other sorts of particles that we won't discuss. But at its most basic level, the action that I have written down is the action of the Higgs field in the standard model of particle physics. And there's also reasonably good evidence that there are other sorts of scalar fields that were involved in the dynamics of the early universe in the first few fractions of a second after the Big Bang. So a scalar field, although it's something that you have not really spent so much time thinking deeply about so far in your lives as physicists, is in fact a very physical thing, which you will encounter cropping up all over the place. Whenever you have an excitation per point in space-time that doesn't transform in any complicated way under coordinate transformations, you have a scalar field. And this is the universal action which will govern its dynamics at long distances. Yes?
I think you said that what you've written is the leading terms of whatever the Lagrangian is.
Yes.
Is there no way to hint, I guess?
Is there... Oops.
That proves this kind of, like, why does it?
The math that proves... No. The math that proves it is the deep and complicated mathematics of dimensional analysis. Okay. This scalar field has dimensions. If you look... And so, okay. So what are the dimensions of the scalar field? This is actually... Okay. I'm not going to successfully manage to do this without setting h bar equals to 1. So this is actually an amusing digression. So let's see if I can come up with a reasonable explanation for why it is that this is the leading term in the action. Well, it's basically an exercise in dimensional analysis. So, you can use more complicated words about renormalization schemes and so forth, but it's basically dimensional analysis. The idea is that a scalar field is a quantity which has dimensions. So how do we determine that? Well, the action is dimensionless. If we use units where C and H bar are dimensionless, so C and H bar will be set equals to 1, the action has units of H bar, okay? And the action is also the integral d4x of the Lagrangian, which was d phi squared plus a bunch of other stuff. So what does that mean? So x has dimensions of length. D by dx has dimensions of 1 over length. So in order for this quantity to be dimensionless, that implies that phi has dimensions of 1 over length. Okay? And in units where h bar and c are equal to 1, energy and mass have the same units. And what are the units of energy? Energy, well, that will go like 1 over length. There are a couple different ways of seeing why that's true. The easiest way of seeing that is that time has dimensions of length, and the energy-time uncertainty relation says that time times energy is h bar, which is equal to 1. So energy has units of 1 over length. Okay? So that means that this field phi has units of 1 over length, or alternatively, units of energy. So, for example, if you wish to write down various other terms that will appear in this theory, then there will be one term in the potential, for example, which goes like phi squared, and its coefficient has to have dimensions of 1 over length, which is to say energy, which is to say mass. So we give a name to that coefficient. We call it mass squared. Indeed, if you, in particle physics, it's precisely the mass of the excitation of phi. It's precisely the dimensionful number that sets the energy scale for the excitations of phi. And now, if you imagine looking at higher order terms in this series, so we're imagine expanding this around the solution where phi is equal to 0, for example. Then the higher order terms, so for example, the higher order term, which looks like phi cubed, will have some coefficient that goes like energy rather than energy squared. And so if you're looking at very low energy excitations of this, then on scales where you're studying small compared to, for example, the mass of the particle, then, or I'm not explaining this terribly clearly. The idea, okay, let me not get too into the details here, but the idea is that the coefficients here in this expansion, and so, for example, you could have another coefficient of order phi squared, d phi squared. Those coefficients are all dimensionful parameters. And so, for example, the phi cubed term will have dimensions of energy. The phi fourth term will be dimensionless. The phi fifth term will have dimensions of 1 over energy, and so on and so forth. And so you can actually argue, I mean, I won't go through the whole argument here, But you can actually argue that if you're studying the physics at a low energy scale, then all of those terms which have coefficients that have dimensions that go like 1 over energy to some power will be irrelevant. So when we talk about the possible terms that we can add in a Lagrangian, there are those terms which are so-called relevant and those terms which are irrelevant. The relevant terms are the ones which have coefficients that have dimensions that are positive powers of mass, positive powers of energy, and the irrelevant ones are the ones that have dimensions that are inverse powers of energy. And the basic idea is that if you're studying the physics of the system at low energies, then it's only those relevant terms which are important. So that's the basic logic of the explanation. So just as an aside, nobody picked up on this yesterday, but when I wrote down the action of general relativity, I said, well, there's only one scalar that you can form from the metric, which will be r. But in fact, there are other scalars that you could form. You could also have r squared, for example. Or you could have some other higher powers of r. But those will be suppressed by some dimensionful constant. And the only natural dimensionful constant which could appear there is the Planck's constant. So they will be suppressed by what's called the Planck mass, which is the natural scale at which higher order corrections will become relevant in general relativity. And so, in fact, you can argue, simply based on dimensional analysis, that in general relativity, the only terms which are relevant in the sense that I have described earlier are the cosmological constant term and the Einstein-Hilbert term. So simply using these dimensional sorts of arguments, you can actually argue that the only terms which will appear in the dynamics of general relativity, if you're looking at length scales that are very long compared to the Planck length, are the cosmological constant and Newton's constant, namely the Einstein-Hilbert term and the cosmological constant term. Okay, you've completely distracted me, however. This is not what I was planning on talking about. But I was only going to say that there are a zoo of possible Lagrangians that you can write down, which will govern the dynamics of a scalar field or any other sort of field. The various terms which will appear in this Lagrangian have coefficients which are dimensionful quantities. And we wish to study the ones which are most relevant when we're working at low energies, which means that in the case of the scalar field, we're considering the kinetic term d phi squared, plus, in general, some potential v of phi. But the most important term in that potential will be this quadratic one, m squared phi squared. Now, of course, you could ask me, well, why don't you have any terms in this Lagrangian which are linear in phi, or linear in its derivatives, rather than quadratic? And the answer is that if I have any such linear terms, I can always remove them by a change of variables. So, for example, if I had a term in this equation which was a constant times phi, I could always shift phi by a constant and complete the squares to turn that into something that looks like phi squared. Are there any questions on that? This was a bit of an aside that I hadn't intended to get into, but it's actually an important discussion. So just to return to where we were, the Lagrangian, or in Minkowski space, before considering the coupling of gravity, the action of a scalar field will be the integral of minus 1/2 d mu phi minus v of phi, where v is some function of phi, which we call the potential. Any questions on that? So this is the basic action that we will start with to start understanding the dynamics of the scalar field phi. So what are the equations of motion for phi? Well, we just take the variational derivative of the action with respect to phi, which is the sum of two terms. So it's the derivative of Lagrangian with respect to phi minus the derivative with respect, the derivative of Lagrangian with respect to d mu phi. What is that? Well, we have minus v prime of phi from the first term minus d mu of the derivative of this kinetic term with respect to d mu phi. So we get a minus 1/2 from that coefficient out front, and then we have the derivative of something of the square of d mu phi. So we have 2 d mu phi coming from the derivative. Or, putting it all together, the equation of motion is d mu phi minus v prime of phi is equal to 0. Or d mu phi is equal to v prime of phi. So this is the equation of motion of a scalar field for the general Lagrangian that we wrote down above, including a kinetic term and a potential term for the scalar field. So this is the sort of equation of motion that we are used to dealing with at this point in our lives. It's a second-order differential equation for the scalar field, and the source term, in general, could be some complicated function of phi that I have written here on the right-hand side. And this equation has a name. It's usually referred to as the Klein-Gordon equation. And I don't want to go too much into the history here, but it's essentially the relativistic generalization of Schrödinger's equation. And in fact, it was invented before Schrödinger's equation by Schrödinger, but Schrödinger didn't quite know how to think about it, and so he only looked at the non-relativistic version, which is Schrödinger's equation, as we usually refer to it. That's the thing that's linear in time derivatives, whereas you can see here, this guy is quadratic in time derivatives. Okay, any questions on this? Well, let's go ahead and couple this guy to gravity. So, in curved spacetime, the scalar field, excuse me, the scalar field action is found by using, again, as usual, our principle of minimal coupling. So, what is our principle of minimal coupling? Well, it says every time we have an integral d4x, we replace that by the appropriate covariant notion of integration. So we just take this equation, and we covariantize it by writing the integral d4x, the square root of minus g, times 1/2 grad mu phi, minus v of phi. So you can see here that the metric dependence of this will enter in two ways. First, it will enter through the overall prefactor of the square root of minus g, and second, it will enter through the derivatives, which we have now replaced by covariant derivatives, which of course depend on the metric of spacetime. Now, of course, you're going to tell me, but Alex, for a scalar field, the covariant derivative is equal to the partial derivative. And you would be right if you said that. So, in fact, for a scalar field, life is relatively simple, and we can just replace those covariant derivatives by partial derivatives. So, if we wanted to be careful, we would just have to remember that the only place that the metric will enter will be because we use the metric to contract together these two indices in the derivatives of phi. So all I have done here is I have lowered the index on one of the covariant derivatives and written out the metric dependence explicitly, and used the fact that the covariant derivative of a scalar is equal to the partial derivative. Okay. So we can now go ahead and write down the stress tensor of the scalar field. So what is the stress tensor of the scalar field? So T mu nu is, I always forget. So we just refer to this equation that we derived last time for the stress tensor in terms of the variation of the metric. So it's minus 2 over the square root of minus g times the variation of the action with respect to the inverse metric. So you can see here that there will be two terms that will appear in the stress tensor. The first of which comes from the variation of the inverse metric here. So what is that? Well, we have a minus 1/2, which cancels the minus 2, a 1 over root g, which cancels this root g here, and we just get d nu phi, coming from the variation of the inverse metric. And then we have a second term which comes because we need to vary the root minus g that appears as an overall prefactor in the metric. And what do we get? We get minus 1/2 g mu nu times the Lagrangian itself, times minus 1/2 d mu phi minus v. That minus 1/2 g mu nu out front just came from our friendly formula for the variation of root minus g under a variation of the metric. So just to summarize, the stress tensor of the scalar field was found by covariantizing our scalar field action and varying with respect to the metric. And what is the equation of motion for the scalar field? Well, the equation of motion for the scalar field is found by covariantizing the equation of motion for the scalar field in flat space. So the equation of motion for the scalar field in flat space was this Klein-Gordon equation here. And we just covariantize it in the usual way by replacing partial derivatives by covariant derivatives. Now, in fact, there's a second way that we could have derived the equation of motion for phi in curved space, and that would be by, again, explicitly varying the action of phi in curved space with respect to phi and setting that equal to 0. And you can check, and I encourage you to do so, that in fact you get the same thing. So this equation that I've written down here is sometimes referred to as the Klein-Gordon equation in curved space. I should emphasize here that I could have replaced this first covariant derivative in the Klein-Gordon equation by a partial derivative, because the derivative of a scalar, the covariant derivative of a scalar is the same as the partial derivative of a scalar. But I could not replace the second guy by a partial derivative, because then you're taking the derivative of a vector, which is not the same as the partial derivative of a vector. So this operator, the second-order differential operator that's appearing on the left-hand side of the Klein-Gordon equation is not the same as it is in flat space. It has some corrections due to the curvature of space-time. And we often give a name to this operator. We often call it the curved space Laplacian. Because if you were in flat space-time, this would be the standard Laplace operator, or I guess I should call it the D'Alembertian instead of the Laplace operator, because we usually call the one with times in it the D'Alembertian, and the one in spatial directions the Laplacian. Often we're a little sloppy with our language, and we just call all of them Laplacians. And this operator that I've written here, which appears in the Klein-Gordon equation, is the curved space generalization of the Laplacian. Now, let me remind you that one of the most important features of the stress tensor is that it is conserved, so that the covariant derivative of the stress tensor, if you contract together one of the indices of the derivative with one of the indices of the stress tensor, is equal to 0. And in fact, I will just let you check for yourselves that the equation of motion for phi can be used to show that the stress tensor is conserved. So if you just started taking covariant derivatives of the stress tensor as I've written it up here, in general, it would not be conserved for an arbitrary scalar function phi. But if phi solves its equation of motion, which I've written down for you here, you can check, and I encourage you to do so. It's a nice little exercise that this stress tensor will be conserved. Any questions so far? So far, I haven't been terribly specific about what my potential V of phi is. And in particular, V could be some horrifyingly complicated function of phi, which would mean that the equation of motion that we have written is something horribly nonlinear. The Klein-Gordon equation would be horribly nonlinear, and in that case, these equations would be very difficult to solve. And so, finding a solution of the scalar field equation alone, much less the equations of the scalar field coupled to general relativity, would be quite a substantial task. However, what I would like to point out is that there is always going to be a very simple solution to this set of equations of motion. So the simplest solutions to the equation of motion will be when phi is equal to a constant, which I will call phi naught. And you can see by looking at this Klein-Gordon equation right here that that will be a solution to the equations of motion when phi naught is a minimum of the potential V. So V prime of phi naught is equal to 0. Now, I said that phi should be a minimum of the potential. Strictly speaking, phi could also be sitting at a local maximum of the potential as well. But as you may guess, that will be unstable for the same reason that if you're studying a standard mechanics problem, if you sit at an unstable equilibrium at a local maximum of the potential, that will be unstable against small fluctuations. So if you wish to look for stable solutions, then you have to set phi to be sitting at one of the minima of the potential V. So what is the stress tensor in that case? Well, let me remind you what the stress tensor looked like. It was d mu phi minus 1/2 g mu nu times the kinetic term. Here, I don't want to write down too many mu indices, so we'll call that d alpha phi d alpha phi along with the potential term. And so you can see that in the case where phi is equal to a constant, all of those derivatives disappear, and we just have 1/2 g mu nu v of phi naught. So, in fact, if you have a scalar field which is at equilibrium, in the sense that it's sitting at one of the minima of the potential, then the stress tensor is very simple. And in fact, this is a stress tensor which is hopefully familiar to you, unless you have an extremely short memory span, because it's a stress tensor that we encountered about 30 minutes ago. It's the stress tensor of a cosmological constant. So this stress tensor is the same as that of a cosmological constant. I told you that the cosmological constant was vacuum energy, which corresponded to the overall constant that you choose when you choose a zero for the potential energy. So this should not be a surprising statement to you at all. But it does mean that when I say that we observe a cosmological constant by observing the expansion of the universe, in fact, what we could be observing is the fact that there is a scalar field in the universe, and we happen to be sitting at a stable equilibrium for that scalar field, where the value of the potential at that equilibrium is not equal to zero. That is, to a large extent, observationally indistinguishable from a cosmological constant. Now, the difference between a cosmological constant and a scalar field is that a scalar field has actual dynamics. And so, if you perturb space-time in some way, you would expect that to lead to some dynamics for phi. And so, this is indeed one of the ways that people try and investigate the implications of a scalar field versus that of a cosmological constant. Indeed, you may have heard of the theory of cosmological inflation, and that is the theory that there was an exponential expansion of the universe at very early times, which was driven not by a cosmological constant, but rather by a scalar field that looks exactly like a cosmological constant to within about a 1% degree of accuracy. So, by and large, in this class, when we try and write down solutions to Einstein's equations coupled to matter, we won't be able to, or we won't be ambitious enough to try some very, very complicated matter. And I believe in this course, when we talk about scalar fields, we will almost entirely be interested in the cases which are easy to solve, where the scalar field will be sitting at or near one of its equilibria. So this was a brief discussion of the dynamics of general relativity coupled to the simplest type of matter, which is a scalar field. And I would now like to discuss general relativity coupled to the second simplest type of matter, that of a Maxwell field. But before I go on to do that, let me pause and see if there are any questions. No questions? Okay. So, what about a vector field or a Maxwell field? So, if we wish to consider a field theory which is not a scalar field theory, then the next simplest type of matter will be described by a vector field, or by a one form. And in fact, you've spent a large portion of your physics career studying a field theory whose degrees of freedom are described by a one form. That theory that you were studying was electromagnetism. So the electromagnetic fields, or I should say more properly, the electromagnetic potentials, V and A, the scalar and the vector potentials, can be packaged together into a one form, which we typically call A mu, whose components in Cartesian coordinates in flat space are just minus V and A vector. So you probably, in your electromagnetism classes, saw that under Lorentz transformations, the vector potential and the scalar potential got all mixed up. They got all mixed up in exactly the way that the components of a one form will mix together under coordinate transformations. So this is often called the one form or the vector potential of electromagnetism. So what we want to do is regard this as a one form, and we will often use the slick notation for one forms where we write them in a coordinate independent way as A being A mu contracted with our basis of one forms dx mu. Okay. If I have a one form, then I can take its exterior derivative to get a two form. So let's just investigate the two form, which is found by taking the exterior derivative of this one form. So this two form has a very interesting name. It is referred to as the electromagnetic field strength. If I can possibly write, it's the electromagnetic field strength. So what are the components of the electromagnetic field strength? Well, if we wrote it out in index notation, F mu nu has two lower indices, and because it's a two form, it's antisymmetric in those indices. So it has the same number of degrees of freedom as an antisymmetric 4x4 matrix. Namely, it has 6 degrees of freedom. And there are 6 fields in electromagnetism, the 3 components of the electric field and the 3 components of the magnetic field. And if you work it out in Cartesian coordinates in flat space, F is nothing more or nothing less than a packaging of those 6 degrees of freedom. Let's see. So F0I is the time derivative, F0I is the time derivative of AI, otherwise known as the electric field. And Fij is the spatial derivative of AI, otherwise known as the magnetic field. So let's see, F12 will be B3, F13 will be, F12 will be B3, F13 will be B2, and there's actually a conventional minus sign there, and F23 will be B1. And then all of the other elements are determined by the fact that F is antisymmetric. So this electromagnetic field strength is a convenient packaging of the electric and magnetic fields packaged together in a way which makes their transformation properties under Lorentz transformations completely clear. You know, at the beginning of your studies of electromagnetism, It would have been helpful if someone had told you that all of the degrees of freedom of electromagnetism are packaged into a 2 form, but it's, the cruel system that we have set up for physics education prevented that sentence from making any sense to you at the time. But in fact, the correct and most elegant way of thinking about electromagnetism is it is a theory whose degrees of freedom is a 1 form and whose field strengths, the electric and magnetic fields, are a 2 form. Yes?
A question. There is something I don't understand, and you could elaborate. Type of matter is a vector field.
Yes.
How can that be?
What do I mean? So remember, what is electromagnetism? Electromagnetism is a theory where your dynamical variables are the electric potential V and the magnetic potential A vector. A vector is a 3-dimensional vector, but you can package the electric and magnetic potentials together into a 4 vector. And so if you wish to think of the theory of electromagnetism, it is a theory whose degrees of freedom are packaged into a 4 vector, or a 1 form. They're the same thing. You just raise and lower the indices. So just as a scalar field theory is a theory whose basic degree of freedom is a 0-0 tensor, and general relativity is the theory whose basic degrees of freedom are a 0-2 tensor, electromagnetism is a theory whose basic degree of freedom is a 0-1 tensor, namely a 1 form.
Do you describe matter or do you describe fields?
When I say matter, I mean matter generally speaking. So sometimes we distinguish between what we mean by matter and what we mean by fields. When I use matter, I mean by matter anything that can appear as a source term in Einstein's equation, namely anything that has energy.
That just means photons, right?
Yeah, photons. Photons carry energy. Electromagnetic waves carry energy. So as far as I am concerned, they are matter. Sometimes when talking about particle physics, we'll distinguish between forces such as electromagnetism and gravity, and matter fields such as those which describe electrons, protons, and so forth. But when I say matter, I just mean something that carries energy. Okay. That's a good question. Any other questions? Okay. Well, now that we know that F is equal to dA, then recall that the exterior derivative has the convenient property that it squares to 0. So we immediately know that the electromagnetic field strength satisfies a first-order differential equation, namely that dF is equal to 0. So if you stare at the components of this guy here, you can quickly work out exactly what this means in component notation. So in Cartesian space, in flat coordinates, this would be the equation which says that the gradient, in the sense of vector calculus, of the B field is equal to 0, and the curl of the electric field is equal to minus the time derivative of the B field. So because F is the derivative of a 1 form, it obeys a first-order differential equation, and we recognize that equation dF equals 0 as just as half of Maxwell's equations. So this formulation of electromagnetism in terms of exterior calculus, exterior derivatives, and differential forms immediately makes it clear that it makes half of Maxwell's equations completely trivial. And in fact, the other Maxwell equations are equally easy to write down. So F is a 2 form, and the only other derivative operator that I could think of writing would be the derivative operator where you contract one derivative with the index of the derivative of one of the indices of F. What is that? that should be equal to a 1 form. We typically give a name to that 1 form. We call it the current 4 vector. Or in components, the 0th component of this would say that del dot E is equal to the 0th component of the current 4 vector J mu, which we call rho, the charge density. And the nu equals I component of this would give you the other Maxwell equation, del cross E, del cross B is E dot minus J vector. So I haven't worked this all out for you completely explicitly. In fact, on your next problem set, the one that I'll hand out the first Monday that you get back, I'll ask you to work this all out explicitly. So, just to summarize, in flat space, namely in Minkowski space R31, the equations of motion of Maxwell theory are the statement that F is the exterior derivative of our 1 form potential, and d mu F mu nu is equal to J nu. So now we plug this into our covariantizing machine and we turn the crank in order to write down Maxwell's equations in curved space. Maxwell's equations in curved space-time, well, what are they? Well, there's still the statement that F is equal to dA, so that dF is equal to 0. And the only place the metric ever appeared was in this derivative operator. So Maxwell's equations in curved space will be the statement that F is equal to dA and grad mu F mu nu is equal to the current 1 form. Okay, so it's a straightforward exercise along the lines of what we have done so far to guess what the correct action of Maxwell theory is. So let's just outline the logic of that argument. So the action of Maxwell theory, so the action of electromagnetism, well, it has to be a functional of the vector potential A. It has to be quadratic in the derivatives of A. And it has to be coordinate invariant. And in fact, if we impose just one more symmetry principle, then the action of electromagnetism will be uniquely determined. So one thing that I would like to point out to you is that if we wrote, so let me rewrite Maxwell's equations as dF equal to 0 and grad mu F mu nu is equal to J nu. If you look at those equations, then by construction, those are invariant under the gauge transformations, where A goes to A plus d lambda. And in fact, you can see that there's only one action that you could write down, which is consistent with this principle of gauge invariance. And that action is just the integral d4x of F mu nu, F mu nu. Or in curved spacetime, the integral d4x of the square root of minus g, F mu nu, F mu nu. And there's a coefficient out front, which is just some conventions, which is minus a quarter. So you can check, and you will check on your next problem set, that the variation of this action with respect to the electromagnetic potential does give Maxwell's equations. And you will also check that the variation of this with respect to the metric will give you the stress tensor of electromagnetism. So did you guys compute the stress tensor of electromagnetism in your EM class? You probably did. Yes? Maybe? Okay, well, you'll compute it on your next problem set, and I guarantee you'll compute it in a different way than you did in your electromagnetism class. So how does this action depend on the metric? Well, we have minus 1/4 integral d4x, and the metric appears 3 times. First, the action depends on the metric through the square root of minus g out front. But we have also raised 2 indices. So there are 2 powers of the inverse metric that will appear if you write everything out in terms of the electromagnetic field strength as a 2 form. And so you just need to study the variation of this action with respect to those guys in order to determine the stress tensor of electromagnetism. I will just write down the answer for you. So here, by f squared, I just mean f mu nu, f mu nu. So this is 1/2 minus 1/4 the integral d4 x root minus g of f squared. So this is the stress tensor of electromagnetism. And we can then go ahead and write down the equations of motion of general relativity and electromagnetism together. And we could even give those equations a fancy name. We could call them the Einstein-Maxwell equations. What are they? They're g mu nu is 8 pi g times the stress tensor of electromagnetism, f mu lambda, f nu lambda, minus 1/4 g mu nu f squared. That's the equation of motion for the metric. And the equation of motion for f is df equals 0, and grad mu, f mu nu, is equal to 0. So I think it's worth pausing for a minute and basking in the glory of these equations. These are a very complicated set of highly coupled differential equations. The electromagnetic potentials appear in the metric equation. The metric appears in the equations of electromagnetism. So they are very difficult equations to solve. But I would like to emphasize to you that gravity and electromagnetism are the only 2 long-range forces in nature. And that in 99.9% of the universe, there's actually no matter present. The matter in the universe is concentrated in this infinitesimal part of the observable universe that we like to focus on, things like galaxies, stars, planets, and so forth. But the vast majority of the universe is empty space. And the only forces which are going to be relevant there are those which are long range. The other forces of nature, the nuclear forces, they all die off exponentially at length scales past the atomic length scale. So if you're looking at physics in the 99.9% of the universe that is empty, and if you're studying it on length scales larger than the atomic length scale, this is it. These are the equations of motion. So I think it's worth just emphasizing that. In your lives as physicists, you spend a lot of time learning little bits and pieces of things here and there. And every once in a while, it builds up, and you can finally understand the complete picture as a whole. And so this is really one of those moments, because you have now understood the equations that govern the only long-range forces that we know of in the universe. General relativity and electromagnetism are the only long-range forces. What do I mean when I say they're long-range forces? Well, the strength of electromagnetism and gravity falls off according to Gauss's law, like 1 over r squared, whereas the strength of the interactions of the nuclear forces, the strong and the weak forces, fall off exponentially with r. So at any reasonable distance scale, it's only these long-range forces that are present. And for the vast majority of the universe, you don't even need to worry about the matter that's present. So 99% of the universe is empty. I think it's fair to say that these equations govern the dynamics of most of the universe. And indeed, you could say of the vast majority of the universe. If you only understood these equations, then you would, okay, maybe you have to deal with pesky little things like stars and galaxies and atomic physics and particle physics and nuclear physics, details like that. But I think it's really fair to say that a huge amount of the dynamics of the universe is contained in these equations that we've written here. So, this really completes what I wanted to say about the basic formulation of general relativity. So I think this is probably a good time to end the class and to send you all off on your winter break. It's not even worth sending it a spring break. But before I do so, let me pause and just tell you a little bit about where we've been in this class and where we're going. So roughly speaking, the first 3 or 4 weeks we did some math, and then in the last 2 weeks or so, we have formulated all of the basic ingredients of general relativity. We've understood the equations of motion, and we've understood the various source terms that will appear in the equations of motion in a variety of different settings. And the remainder of this class will be devoted to a study of the solutions of these equations in one context or another. So when you come back from your break, we'll start with a lecture discussing how a general technique for solving Einstein's equations. So Einstein's equations are, of course, horrible and very difficult to solve exactly. So what we will do is we will start discussing the theory of symmetries in general relativity, and we will understand how the presence of some geometric symmetries will simplify the solutions of these equations. And we'll then proceed to discuss one of the most symmetric solutions of general relativity, namely that of the Schwarzschild solution. So the Schwarzschild solution is that geometry which describes space-time in the presence of a spherically symmetric static object. And we'll spend a good deal of time, we'll probably spend about a couple weeks studying the Schwarzschild solution, because along the way, we will understand all of the basic tests of general relativity involving solar system physics before moving on to the study of black holes. So we'll spend about 2 weeks or so studying the Schwarzschild solution in all of its gory detail, along with the basic tests of general relativity, before spending roughly a week each on 3 sets of special topics, a week on black holes, a week on cosmology, and a week on gravity waves. So that's where we're going. I think this is probably a good place to stop, but maybe let me just see if there are any questions before we go. All right, I'll see you in a week. Thank you.